Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the basics of carbohydrate. In the basics of the carbohydrate, we discussed about DL configurations. What do you mean by the D or L configuration? As we know that D and L are the relative configuration, and these relative configurations are assigned according to one glyceraldehyde is taken as a reference compound, and as we know that glyceraldehyde is a triose because it containing as a 3 carbon atom, and therefore according to as a IUPAC name, the name of that compound is a aldotriose. Triose indicate as a 3 carbon atom, and last suffix OAC indicate as a sugar unit. And as we know that according to as a definition, carbohydrate means polyhydroxyaldehyde or the ketone optically active compound on hydrolysis produce the unit. That type of the compound is called as a carbohydrates, and the simplest one is a carbohydrate. So relative configuration we have discussed about that, and by using after that how to derive, and as we know that pentose and the hexose are the most frequently or the naturally or freely present in the nature in the free state as well as in the combined state, that we know that. And most importantly, we are learning the structure of the glucose. We according to and generally carbohydrate compounds or the chemistry is mainly studied on the basis of Fischer projection formula. And as we know that how to represent that compound, and the carbohydrates are written vertically, and during that DL configuration we have know that OH it is present on right hand side, then we can designate it as a D configuration. If suppose OH is on the left hand side, then we can call it as a L configuration. These are the simplest notation used during the configuration. These are the what we can call it as a system nomenclature system for assigning that. So today what we are going to learn, that is the basics of carbohydrate, that is the discussion of the point. So in that we are talking about plus glucose and aldohexose. Aldohexose is a common IUPAC name, and glucose is a common name. And as we know that the glucose, the structure of glucose, why it is called as a D series, D configuration, that we already learned. But here collectively what we are going to talk about, what do you mean by glucose and aldohexose, because it is the unit of which starch, cellulose and glycogen are made up, and because of its special role in biological processes, plus glucose is by far the most abundant monosaccharide. There are probably much positive glucose unit in nature any other organic group, and by far the most important monosaccharide. And most of what we need to know about monosaccharide we can learn from the study of just this one compound, and indeed from the study of just one aspect and its structure, and how that structure was arrived at in learning about the structure of plus glucose, we shall at this same point learn about its properties, since it is from these properties that the structure has been deduced means derived, plus glucose is a typical monosaccharide, and so that in learning about its structure and properties we should be learning about the structure and properties of other number of this family, but plus has the molecular formula, plus glucose has the molecular formula C6H12O6 as shown by the chemical analysis. And now let's see collectively how this, as we know that the structure of that glucose, generally we are writing the structure of glucose is this one. This is a CHO, and then 1, 2, 3 and 4 generally we are writing, and here CH2OH, and as we know that this glucose plus glucose or D-glucose we have derived from the arabinose. Here OH, here also OH, here H, HO, H, then OH and H. This is the general structure of glucose, or plus glucose, or what we can call it as D plus glucose. And now when this glucose, when treated with some of the compound, like here we are going to learn today some of the chemical properties together, we are treating this compound. Suppose this compound is, this glucose is treated with phenylhydrazine, like this phenylhydrazine C6H5, then NH2. As we know that this phenylhydrazine, what type of the product it form, that as we know that this is one of the ammonia derivatives. So this is going to attack on that carbonyl carbon, so that only one carbonyl carbon is present there. This type of the this was inferred from this reagent when we are treating that glucose in with this ammonia derivative, this one, what you are going to get, there is a derivative you are going to, in short I am writing here CH double bond N, then NH and pH, I am writing here CHOH 4 times and this CH2OH. In short we are writing, because we are going to show some of the properties regarding this glucose phenylhydrazone. This is called as a glucose phenylhydrazone. This is a glucose phenylhydrazone. Phenylhydrazone. This is a reaction. One more exam, very good reaction when that phenylhydrazine is treated with, we are getting as this type of the compound. Now as we already learned this one, but collectively here we are going to see Br2 in presence of H2O water. This is a mild oxidizing reagent, we know that this one, mild oxidizing reagent, and that what the mild oxidizing reagent will do over here, it will oxidize the aldehyde group, remaining thing remains as it is. After doing that, what you are going to get? You are going to get this aldehyde group is going to convert into as acid, then CHOH 4 times and then CH2OH. In short I am writing this is a gluconic acid we are getting over here, C double bond O CHOH and 4 times CH2OH. In short, because this generally we are representing CH2, then what we are writing here CHOH, because there are the 4 secondary alcoholic group present in the alcohol and 1 primary, and for writing that reaction, in short we can remember this is a whole reagent. Instead that you can remember this is the structure, glucose structure, where we can carry out this reaction and we will get as this type of the main reaction we are talking. This is a mild oxidizing reagent. What the mild oxidizing reagent will do here? It will convert the aldehyde group into as a carboxylic group, and the resulting compound obtained is a gluconic acid. That is the thing happening over there. And now this reagent further, if you use here dilute HNO3, this is a what we can call it nitric acid. This is generally performing as a or using as a dilute HNO3. It is a strong oxidizing reagent. And what the strong oxidizing reagent do here? It will oxidize this aldehyde group as well as primary alcohol, and it produce this one COOH, then CH, again is a 4 time, and COOH. The compound we are getting is called as a saccharinic acid, right? This is called as a saccharinic acid, as we know that, or that is a saccharinic acid we are getting over here. What? Because on both the side, here we are getting as a gluconic acid, here we are getting as a saccharinic acid. Saccharinic acid means what? Aldehyde group as well as primary alcohol also get oxidized to convert aldehyde group as well as primary alcohol into as a carboxylic group, and the resulting compound form is called as a saccharinic acid. Got it? Now when this compound, when treated with the reagent like as a Ac2O, acetic anhydride, what do you get? And here you are going to get CHO, CHO aldehyde, as well as here we are going to get CH, then O, CO, CH3, here 4 time, and then CH2O, CO and CS3. This type of the compound we are going to get, and this is called as a glucose pentaacetate. This is called as a glucose pentaacetate. So that is the compound we are getting, that the derivative we are getting here is a glucose pentaacetate. Glucose pentaacetate. Glucose pentaacetate gives you this penta-O-acetyl glucose. We can call it as a penta-O-acetyl penta-O-acetyl glucose. Acetyl glucose you can call it as a, either you can call it as this or this one. This one the easiest way to remember that one. Penta indicate as a whatever hydroxyl groups are there. Look at there, number of hydroxyl group present. If you observe this reaction, if you look this D plus glucose here carefully, what do you see over here? There are 1, 2, 3, 4 and 5. There are 5 hydroxyl group. How will you import 5 hydroxyl group present in the glucose? When you treat this glucose with acetic anhydride forms pentaacetate glucose, and this clearly inferred that the glucose containing 5 hydroxyl group. So that is the reaction we have seen over here. And now let's move on to the next reaction over here. Suppose this is treated with here H2 in presence of the nickel, H2 in presence of Rane nickel. What does it give? Here glucitol or the sorbitol we are going to get. Look at here, in the aldehyde there is a one aldehyde group is present, and that aldehyde group is going to convert into CH2OH, then CHOH 4 time, and then CH2OH, right? And now this is called as a sorbitol. This is known as a sorbitol, or we can call it as a glucitol, or you can call it as a glucitol. So that is a what we can call it as a name of this compound after the reduction. Reduction product gives you this type of the compounds are there, and the name of that compound is a sorbitol or glucitol. If you observe this derivative here, after the reduction, the glucose has one aldehyde group, and that is going to convert into as a alcohol, primary alcohol. There are two primary alcoholic group present, and 4 are the secondary alcohol. They are as it. These are the sum of the reaction. Now after this this one, when treated with some other two reagent, acetic anhydride, or what we can call it as a here let us see. After, let me clean this board over here. So now I am writing here, let us clean the board over here first, and now I am still continuing that reactions with some other reagents. So till see here, so here what H2 in presence of the nickel, what it will convert, it will convert that aldehyde group into as alcohol, then CHOH 4 times, and then CHOH. This is called as a sorbitol or which is known as a glucitol or glucitol, I think glucitol, okay. The sorbitol and the glucitol, not tol, I think, all sorbitol or glucitol. OL indicate as a hydroxy group, that is the name over there. And now when this reagent, this one, when it is further treated with acetic anhydride, what it will give? There are 1, 4, 5 and 6. There are 5 hydroxy group present in that sorbitol. All will get oscillated with that acetic anhydride is a very good reagent. Oscillation reaction takes place, esterification takes place, and the resulting compound form will be this one, CHOAC you can write, then CHOAC 4 times, and then CH2OAC. This is the derivative we got over there, that is called as hexaoacetyl glucitol. Hexaoacetyl glucitol. So that is the name of that compound, or we can call it as a hexaoacetyl sorbitol, or you can call it hexa means 6, hexaoacetyl sorbitol. You can call either, you can call this way or you can call it as this way. Both are the same one. And now when this compound, when further treated with HI, heat it. For heating with hydrochloric iodide, the resulting compound form will be this one, CH3, then CHI, then CH2, therefore 3 times, then CH2OH, CH not to C. Here also as a again as a CH3, that the derivative obtained, that is called 2-iodohexane. 2-iodohexane, that's the derivative obtained after treating that sorbitol or glucitol with hydrochloric iodide, heated with, what is happening? This primary alcohol get converted into as a hydrocarbons, then one of the hydroxy group at iodide, and then 2-iodohexane, that if it is heated further for long time, it produces as a N-hexane, I think so. And now these are the compound we are getting over here after the hydrolysis. And now one more, if it is treated with hydrogen cyanide, HCN, what is going to happen? Again cyanohydrin derivative is obtained here. There you can write here again is a CN, then OH, H, then CH, OH 4 times, and then CH2OH. One more hydrogen atom, that is called as a step-up reaction. In a Kiloley-Fischer synthesis, we have learned such type of the compounds are there, and when this is there, if you hydrolyze it, H2 in presence of H plus, what is going to happen? There is a step-up reaction. This cyanide group get converted into as a acid, and we will get CH-OH 4 times and CH2OH. That is the compound we are getting over here. And when this is further treated with HI, this is further treated with hydrochloric iodide, it gives this type of the compound. There is a COOH, then CH 2 4 times, not 4 times, 5 times, CH3 5 times, and there CH3. That the compound we are getting over there, that is called as a heptanoic acid. Hept means 7 carbon atom in the stage, 1, 2, 5, 6 and 7, heptanoic acid. This is known as a heptanoic acid. That the compound we are getting over here. How we are getting these reactions? So all reaction we have seen together with that glucose and aldohexose. Now let us move on to the next point. Next, what we are going to learn, that is a minus fructose or 2-ketohexose, that we are going to learn over here. So whatever reaction we have learned here, all with the plus glucose, and all are the what we can call it is a physical properties of that glucose. Now we are moving toward the next point, and the next point of discussion is this one, that is a minus fructose 2-ketohexose, 2-ketohexose. So that is the point of discussion over here, or that is the content we are discussing over here. That is the point we are discussing here. Whatever we have seen about that plus D-glucose, or this is a minus fructose. Minus means this type of the organic compound rotate the plane of polarization through left hand side, and that's why it is designated as minus D-fructose. And you might be knowing the minus D-fructose means it is generally I think 92.3 degree, that much minus rotation, specific rotation is observed during the experiment. Now let's see the about this minus fructose or 2-ketohexose. The most important ketose is minus fructose, which occurs widely in fruits and combined with glucose in the disaccharide sucrose, that is a common table sugar. The following sequence shown that minus fructose is a ketone rather than an aldehyde, and gives the position of the keto group in the chain. Let us see the structure, how the structure of fructose can be drawn here. CH2OH, and here 2 ketose means a 2 position carbonyl group, then CH, OH 4 times means here I am writing that is specifically here 1, 2 and 3 are there, and fourth one is the CH2OH. Now OH on that side, and here is a OH and OH. One OH secondary alcohol is a, suppose that is a what we can call it as a oxidized, we are getting as a this type of the carbonyl. So number of carbon atom present in the fructose 1, 2, 3, 4, 5 and 6. There are the molecular formula of glucose as well as fructose are same because they are the isomers of each other. Isomers means what? Having same molecular formula but different structures are known as isomers, and that phenomenon is known as isomerism. So fructose and the glucose are isomers of each other. In a glucose there is a aldehyde group, or they shows the property similar to as a aldehyde, whereas that keto group showing as a ketone group properties. So let us see here, the carbonyl group is present when it is treated with the compound like as a hydrogen cyanide, as we know that SCN hydrogen cyanide, it will form the cyanohydrin derivative, and that derivatives are generally is here CH2OH, then this carbon atom OH you can write here, or hydrogen atom here, either this side or that side, it doesn't matter, or we can write here, okay, now let it be HO here, and here you can write CN, and here rest of the thing remains as it is. Three things remains as OH, HO, H and H. This one is the CH2OH. This remains as it is, and after that what you are going to get over here, after this you will see over here, after the hydrolysis, it is a process where the cyanide group, it easily hydrolyze, gives the carboxylic group over there, this one. And what you are going to get over here you are going to get CH2OH, then here HO, then this COOH get cyanide group C triple bond N get converted into as a carboxylic group, and rest of the thing remains as it is like this. So CH2 and this OH, there OH, H, and here HO and hydrogen atom, they are as it is we are getting. So this is the compound we are getting, and when it is treated with, when it is heated with that HI, hydrochloric acid, hydroic iodide, what it will do, all the carboxylic group type of the compound, they get reduced and that converted into as a what we can call it as a hydrocarbon, so that here you are going to get the property CH3, then COOH, then here 1, 2, 3, this CH2 3 times, and the rest is a CH3. That is the compound we are getting. The name of this compounds, this is a cyanohydrin derivative. This one is called as a cyanohydrin derivative. Cyanohydrin derivatives that we got, and here what we got, the name of this compound is a hydroxic acid. This is a hydroxic acid. Hydroxic acid, and this one final product which we got, that is alpha methyl caproic acid. This is called as alpha methyl caproic acid. That is a common name is given to that compound, and that's why this is written over there, right? So these all about the what we can call it as a thing regarding that reactions. And now stereoisomers of plus glucose, nomenclature of aldose derivative, that we know that the structure of that glucose CHO, CHOH 4 times and CH2OH, and as we know that according to as a Hornsop rule 2 raised to n isomers, and here if you remember 2 raised to 4 is equal to 16 isomers are possible when n is nothing but as a chiral center. There are 4 chiral center present in the glucose, and chiral center means what? Carbon atom carrying 4 different group is known as a chiral center, and these glucose generally represented according to as a what we can call it as a glucose structure. So if you see over here, so now again moving toward that, we are talking somewhat about that glucose, because glucose is a very important as far as carbohydrate chemistry is concerned, and that's why we are talking about that one. Suppose as a glucose generally is according to as a Fisher projection formula. Generally we are writing glucose structure is this way. You are familiar, you are very good at drawing that glucose molecule here, OH, then HO, H, then OH here, H, and H. And according to as a Fisher projection formula, and generally those group at the top, they are shown. So they are shown by the dotted line over there. Suppose here you can show that CHO behind, and then OH remain, that OH are coming above the plane, that like this, and here also OH, then this one is a HO here, H here, again here OH, and here hydrogen atom, here again is a OH, here is a hydrogen atom, and the group which is behind is generally written as a CH2OH. This is a simplest representation of that glucose molecule according to the Fisher projection formula. Horizontal lines represent bonds coming toward us out of the plane of the paper, and vertical lines represent bonds being away from us behind the plane of the paper, and the dissimilarity of the two ends of an aldohexose molecule prevents the existence of meso compounds, and hence we expect that there should be 2 raised to 4 16 stereoisomers, 8 pairs of enantiomers. All 16 of these possible stereoisomers are known. Only 3 plus glucose plus mannose and plus galactose are found in abundance. Oxidation effect of alkali reactions of glucose that we will see in the next time. I think we have seen so many reactions, but that are the reaction which are like as filling solutions are the Toulin's reagent. What you are going to do, what you are going to get after treating this solution on the glucose molecule, and what you are going to get, that type of the reaction we will see tomorrow. Let us stop today here, I think, and remaining we will see in the next lecture. Thank you. Have a nice day.